Hello, my name is Steve Miller. I'm a math professor at Williams College, and I want to talk to you today about some fascinating properties of Pascal's triangle. So the way Pascal's triangle is generated is you start off with two diagonal columns of ones, and then every number in the interior is the sum of the two numbers above it. So 4 would be 3 plus 1, 15 would be 5 plus 10. So Pascal's triangle and these numbers have a lot of combinatorial interpretations and meanings. They appear in a variety of problems. One of the most famous is if you're expanding x plus y to the n, then the nth row of Pascal's triangle is going to be the coefficients. So for instance, x plus y squared is x squared plus 2xy plus y squared, x plus y cubed, x cubed plus 3x squared y plus 3xy squared plus y cubed. So while there's a lot of things we could look at Pascal's triangle, today all I care about is a very simple thing. Let's look at the numbers and see whether or not they're even or odd. And let's see what kind of structure emerges. So this is a very coarse way of looking at the data. Sometimes when you have so much information staring at you, it pays to step back a little bit and look for some broad general features. So what I'm going to do is if it's an odd number, I'm going to fill it in and leave it. If it's an even number, I'm going to delete it. And so I wrote a little Mathematica program to generate Pascal's triangle, putting in rows by rows and only looking at what happens, whether or not I'm an even or an odd. And just to make things a little bit easier to plot, I'm going to plot it horizontally, so I'm going to rotate it a couple of degrees, and I'm going to always rescale it so that my image stays on the same size. And so over here, I'm at the first row. I'm going to keep adding rows, and you can start to see very quickly a structure emerging. And what you can see is what's actually known as a fractal. And so you see this piece over here repeats and is here and here, then this bigger block repeats and is here and here, then this giant block over here is going to repeat and be here and here, and so on and so on and so on ad infinitum. And by rescaling this to have something now between 0 and 1 essentially, I'm going to get a fascinating object. This is known as Sierpinski's gasket or Sierpinski's triangle. And it turns out that the dimension of this object is going to be strictly between 1 and 2. What does this mean? By the fact that its dimension is greater than 1, it's thicker than a line or a curve, but it's not as filled in as a square or something with area like a filled-in triangle. And so in some sense, this gives you a sense of measuring the complexity of what's going on from all these cut pieces. And so what I can do now is I can use the manipulate function and speed up time a little bit more and just let this thing run. And so it's a fun problem figuring out how to calculate these numbers quickly, how to build these images. I hope you enjoyed this.